Yeah, good afternoon, everyone. Today we have Dr. Awais Ahmad with us. Now I request Professor Vineet, Assistant Professor of the Department of Mechanical Engineering, Adi Shankara Deemed University, to introduce our chief guest to the gathering. Sir, please.
Good afternoon, everyone. I am B.C. Vinith, Assistant Professor in the Department of Mechanical Engineering at Ashankara deemed to be University, Godu, Andhra Pradesh. It gives me a great pleasure to introduce our distinguished resource person for this session, Dr. Awais Ahmad. Dr. Awais Ahmad is top 2% scientist in the field of material science and chemistry in the year 2023 and 2024, working as associate professor at the University of Salento, Italy, as well as assistant professor at the Department of Chemistry at the University of Lahore, Pakistan. His work focused on nanomaterial synthesis and their application towards heterogeneous catalysis, mainly energy conversion and wastewater. He has published 150 plus SCI papers with a cumulative impact factor more than 2000. Dr. Awais Ahmad also edited more than 9 books, specifically in LC Wire, and also holds academic editorship in various journals such as Nanotechnology Reviews, International Journal of Energy Research, Chemical Data Collection, and in many as guest editor. He is also serving as advisory board member of different journals such as Environmental Research, Clean Technology and Environment, and Materials Today. He is also working as a research fellow professor at INTI University, PSL France, and Kanghi University. On the behalf of the organizers and all the participants, I extend a very warm welcome to you, sir. With these words, now I extend, I hand over the session to our esteemed resource person, Dr. Awais Ahmad. Thank you, sir.
Thank you so much for this brief introduction about me. But in fact, I'm just Awais Ahmad, so it's not a problem if someone's called me Dr. Awais or just Awais Ahmad. So definitely, it's a wonderful event which have been organized with this platform, and I'm very glad to see the very great scientist over there, just like Manoj Kumar, who was dealing this conference in a very good way. Before I start, I must say to the students that don't get bored. I will not make you more bored like others. So this topic is not only that I have to represent my research work. It is the research discussion between you and me that we have to discuss the research gaps, that what we are actually doing and what else we can do in the future, and what the future collaboration can be happen with the students and also with the faculty as well. So with not wasting more time, let's come to the research topic, which is next generation interconnected porous nanomaterials for clean energy. Now, we will just discuss about the energy conversion and how energy is focusing in the different fields and how it's incorporating their behavior and their dilemma in the nanotechnology. Basically, we are dealing with the 4 research topics in which mainly we are dealing heterogeneous catalysis, nanoscale chemistry, we are also doing green chemistry, and then we are fabricating the energy storage devices. Already you get introduced. This is my research group as well, Nano Hydro Energy Group. You can check this on the website as well. My group members, we are working under me as well and on the different projects with the students. Some of the awards, I will just move these, and these are the books if you want to read about nanomaterials and their basic knowledge that what is going on. Some of the high impact factor papers if you want to read. So what will be the outline? We will explain this in our next slides, that what is nanotechnology, what are the nanomaterials, and how these interconnected porous materials are currently showing. So definitely we we are from the Asian side, and the major problem of the Asian side is the energy crisis. Like
So sorry for interruption.
yeah.
You can go for a full view of the PPT, Professor.
What? Okay.
Yeah,
Just
yeah.
one minute. Yes. Is it fine now?
Not yet, Professor.
Is it okay?
Not yet, Professor. Not yet. Still shows in editing.
Now?
Now it came out, Professor. The presentation came out.
And now?
The presentation is not visible now, Professor. I think it came out. It came out of the
Okay.
presentation.
Just a minute. Okay. It's gone out. Okay.
Yeah.
Okay. I'm sorry, guys.
You can share the entire screen, Professor. Otherwise, if you share only PPT, it will show that like the download.
Is it okay now?
Again, it is showing like in the editable way, Professor. Professor, my suggestion, you please share your entire screen and then you share the PPT. And you can go for a full view, then it will be shown. Otherwise, it will
Now it's okay or not?
PPT is visible, Professor, but it is not in a full view. It shows that in what we do in editing, no, Professor, that way it is showing. So what I suggest you, please share your entire screen, Professor. You please go with share entire screen, and then you open the PPT. If you share only the PPT, then it will not be shown like this in Google Meet. It is a problem with the Google Meet.
That's the point. When I was sharing, just 1 minute.
Yeah. You please stop sharing, Professor. Yeah, you stop sharing. Then,
okay.
Yeah. Then you share again. Go for sharing.
Now I have, because I have the MacBook. Now it's showing me allowed to share window, allowed to share screen.
Allowed to share screen, Professor.
Okay. Allowed to share screen, and here this is the screen which I wanna show.
Then you go for
yes. Now you guys can see my screen, right? Is it fine now?
Yes. Now it's fine, Professor. Now it's
fine.
Exactly fine.
We achieved our goal. Okay.
Yeah. Please go ahead, Professor.
I'm sorry for this interruption, students. Okay. So what is the basic problem right now in the Asian country mostly, and even in the European Union as well? Because last month we have a meeting in the summit 2025, which was held in Rome, Italy, and it was also one of the hot topic over there as well, that energy crises right now are really trending. Why? Because we are utilizing a lot of energy, the energy economy, there is no security of energy, and lot of social energy issues which are creating every day, every time. We are cutting trees, we are making more societies because the civilization have been increased. So a lot of problems is happening right now in the world just for the energy crisis. And in that point of view, these are some of the points which are really very dangerous as well, such as resource security, like depletion of non-renewable resources. Like now we are using a lot of coal, gas, natural gas, just for the cooking purposes, and we are depleting the methane in the air as well. Then geopolitical factor as well, you can say the political instability in our tropical regions, and that's the basic reason of natural disaster as well, which we are seeing right now in the Asian countries, just as floods, which are right now really bad situation in the many countries. So what is the target of our lab? That we are developing our research design on the sustainable development goals, and we make sure that what we are thinking, that we have to create something affordable and clean energy for the future perspective of our research. And that's the basic design of my student as well. So in that point of view, we think about that what is the green chemistry. So if we come about what is the green chemistry, that we have to synthesize via green method, we have to use renewable resources, we have to incorporate with the sustainable industry, We have to use the solvents which will be safer rather than dangerous. We have to use the protocols which should be the pollution prevention. And then we have to give the education to our newcomer students and researchers that what actually the sustainable thought is this. And then we have to make our protocols in the green energy concept. So this is the what basic thinking that which we have to adopt, and students have to adopt in their future research as well, just to be greener and be more productive in term of research. So what we are dealing is the heterogeneous catalysis, basically that why we are thinking about the heterogeneous catalysis, because right now the most of the chemical reaction are focusing on the heterogeneous catalysis. Why? Because in the heterogeneous catalysis we get kinetics, we get the surface morphologies, and that is the basic theme to get more productivity, because the inorganic synthesis catalysis are more productive as compared to organic. And in that point of view, heterogeneous catalysis is far better than homogeneous catalysis in energy conversion and management. Now, we definitely know that, in fact, when we are thinking about some technology, the first point which comes to our mind is nanotechnology. And why nanotechnology is so in is that because it's very diverse in feature. Just like you can say that, just like Indian actor Salman Khan, he's diverse in his features. So the nanotechnology is also diverse in his features because of its families. Right? Because there are three types of families which exist in the nanomaterials. Number one is inorganic. Now, the inorganic nanomaterials is basically the product table D block elements, the transition and inner transition materials. These can be happen to be synthesized like zinc nanoparticles, chromium nanoparticles, silver nanoparticles, platinum nanoparticles, cadmium nanoparticles. These are the transition and inter-transition materials which can be designed for the metal chalconides and quantum dot as well. If we go with the organic nanomaterials, now it's come to the micelle, liposomes, nanocapsules, nanospheres, dendrimers. And the third and the most interesting is the carbon nanomaterial, which is more productive in energy conversions, that is graphene. And the most favorite for the ladies, if the ladies are in the meeting, the diamond, because it's the precious gift for a lady. So the diamond is a pure carbon, is the purest property of a carbon known as diamond. And the other feature are fluorescence, carbon dots, graphite, and graphene as well. Now, how these nanomaterials can incorporate this behavior in terms of sustainable threats, which we have right now, like the energy conversion threat, because of their diverse feature defined, because of their interconnecting structures, and because of their 0 to 3D dimensions. These features actually let them in the list of the top that they can act as a greatest material for energy conversion. And what is actually nanomaterial? Now here is a very beautiful example for you guys that what is actually nanomaterial. Now in the first, if you see the block, this is the first block, it is a bulky material. Now the bulky material surface area is 54 inches square. I think so. If you guys are from mechanical department, you are more expert in this inches per inch squares. Now, if you cut the box into 4 pieces, now the surface area and the phases get increases, because now you have 8 blocks and 6 phases. In the first, you have just 6 phases and 1 block, but now you have 8 blocks. So the total surface area increased from 54 to 108 inches per square. If you make some more blocks, like if you cut it more, then it came to 27 blocks and the surface area get increased more. So this is the nanotechnology that we are actually coming out the block sides of the bulky material, and we are flourishing the material and making its blocking sites to the active sites. So this is what nanotechnology do with the catalysis. There are typical 3 methods to synthesize nanomaterial. Number 1 is chemical, number 2 is physical, and number 3 is biological. Now, in the chemical method, you can design your material via hydrothermal, via polyol process, via chemical reduction method, and sol gel, microemulsion, and precipitation method. The physical method is the method like some of the material don't want to be in the nanomaterial range. Just like if you have a brother or a sister who don't want to study in his earlier career, what you guys do, you guys give the pressure. No, you have to do study, you have to do the study. So it's the physical torture. Same what we do with the nanomaterials. If they don't want to be synthesized to be nano, we give the physical torture, just like microwave radiation, sputtering, thermal decomposition, sonochemical, just like that. And the third and the most, what can I say, is the eco-friendly, is biological method in which we deal with the green synthesis of material. So what is the energy storage mechanism and how it is happening, that why it's so in right now? So the energy storage mechanism basically deals with the four properties, which is battery, supercapacitor, hydrogen storage, and fuel cell. And in every concept of the energy storage, you get the different key roles of your nanomaterial. Now, on the battery, the basic chemicals like lithium, zinc, potassium, because now we are working on zinc air batteries as well. So what is the key role is to improve the charge and discharge the rate. You have to improve their charge and discharge rate. In the next slides, I will explain the research activities which we have done, that how we are actually doing this charging and discharging mechanism. Second one is the supercapacitor. Now it is somehow electrostatic plus chemical reaction, and you have to increase the surface area of your ion storage, which is actually happening inside of the capacitor. Then fuel cell, it is completely energy from chemical to electrical. Your catalyst should be doing the hydrogen chain reaction to make fuel cell. And the fourth one is hydrogen storage, or you can say hydrogen generation, is just the deposition, or you can say the adsorption and desorption mechanism of your catalysts. So in the first, magazine. Now the magazine are right now a very trending material, because it has been invented by Yuri Gogostri in 2003, that these materials can be more active in terms of energy storage mechanism. Now, why it's more active towards the supercapacitor? Because in the back slide I explained, in the supercapacitor you need the ion storage, you need the oxygen vacancies. So if you get the oxygen vacancies, the flow of electron will be faster. And if the flow of electron will be the faster, you will get the more energy density. And if the energy density will be higher, the binding energy will be decreased and electron will move faster. And here you can see just the results about the potential with term of the current density, that with the 75 microvolt per second, we get a symmetric supercapacitor application. Now here, this explains you that your capacitor is symmetry or asymmetric. If these peaks are irregular, then it's called asymmetry. If these peaks are regular, then it's called symmetry supercapacitor. And at the end, you have to check that your diffusion rate, what can be diffusion rate with the cycles, and we check with the 1000 cycles of our material with the capacitance reaction, and we get 87.1% of capacitance of this material. What was this material? This was, we derived the gadolinium with magazine. So it was the mixture of inorganic and interconnected porous material. This is one of the very favorite research paper which we publish, and it's also patent with the US, that mesoporous nanowires we derived for the very first time. Was the first one we derived it with the chromium cobalt. And in the chromium cobalt, we just use it and we get just like the very sharp nanowires of 15 nanometer. And if you check the just the elemental identification, you can get that we get cobalt 6% and chromium is near to 16%. Now, if we check the storage mechanism in this material, what was the interesting behavior? That we get all of three types of material. We get pure capacitor, we get pure battery, and we get a new type of aqueous hybrid supercapacitor. So in the first, you can see here the cobalt reaction, which was dominated by surface redox reaction. You can see here and here, the both are happening on the same time, oxidative and reductive reaction. So it is a battery type. And if you see this one, so it is dominated by layered, because here you can see the layer by layer. So it is dominated by double layer type. So it is known as pure capacitor. And if we mix together, which was our material, it's chromium cobalt nanowires, it happened that it behaved for the both capacitor and batteries. So that's the reason we called it aqueous hybrid supercapacitor, which have the behavior of both side reaction. And it in the end, we get the more synergetic effect nature from battery type to hybrid type. In that scenario, we design metal organic framework. One of my student she's currently working on new type of metal organic frameworks, that can we switch new type of metal organic frameworks, because we was inspired by Umar Yagi, who was in the previous time invented these MOFs like MIL 101, ZIF 8, ZIF 67, MIL 100, and there are multiple ZIF 100, MIL 100 as well. So we are right now also focusing on this, that how MOFs can work towards the green chemistry. And in that scenario, we design a silver MOF for asymmetric supercapacitor. Now, in the previous, I show you a symmetric supercapacitor. Here you can see a asymmetric supercapacitor. You can see here the asymmetric supercapacitor behavior, which change to which we check with our electrode, and at the end we get like more than 92% supercapacitor activity on the nickel form. And here is a little video which will be really inspired, that we designed this material, and at the end we test this material on our coin cell application, a real cell application. With it was a project with Casio. So just watch this video. So here we just incorporate our coin with a simple Casio calculator, because your coin will be not wasted, it can be charged every time. So now you can see that the calculator is working on with the help of this coin cell, and this coin cell can be charged more than 1,000 times and can work for almost 10 to 15 days with this one charge. I will just move a little bit forward. So this is the one of the very great example of the coin cell application. And in that scenario, we design also the double layer MOF, which was very tough to design, because it's very tough to organize such a sort of double layer MOFs and stabilize them, because you are mixing two MOFs. So we design ZIF 8, ZIF 67, two birds with one stone, and we get asymmetric. You can see here the peaks. It's the asymmetric supercapacitor, and at the end we get 96.8 supercapacitance with the 50,000 cycles. And it was the one of the best article we have ever produced, like with the 50,000 cycles. So let's explain a little bit about the green synthesis, that what is actually the green synthesis. No, the major concept of the green synthesis is to control the size of metallic nanoparticles, because the major drawback of every research is that how to control the size, because the size agglomeration is very fast, because nanomaterials are not stable in term of their stability. So in that scenario, we design green synthesized metallic nanoparticles. And how we can get it, because you can get the metabolites, phenol oxides or terphenides, which act as a caping agent and which can control the size of your metal nanoparticle. And in that scenario, we design the growth of zinc, silver nanowires, and we get some catalytical reduction. I will just pass on, and because it was not on the topic. So in that point of view, once we think about some organic chemistry reaction, that how we can incorporate the biofuel production for the next generation materials for energy storage. So in that point of view, we think about the biomass valorization, which was one of the very interesting topic in the recent research activities of my one master and PhD student. And in that scenario, we design furfural, we convert furfural to cyclopentanone by using alumina SBA catalyst. And in that scenario, we make sense that how we can use waste to energy, like, and waste to pharma, like, because we have a lot of waste in our Asian countries. So how we can utilize this waste in terms of this energy or biochar composition. And then that's the basic point of view. We design materials for photocatalytical hydrogen production, because we get the coffee beans in the first time, and we design very first time the silver coffee beans reaction for 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 hydrogen production in term of energy conversion management. And this was the one of the hydrogen cycle which we designed, that which type of cycles we can adopt in our future research works. And in that point of view, we design biomass based material for HER, hydrogen evaluation reaction, and ORR, oxygen revolution reaction. And in that scenario, we get 1.29 onset potential with the slope of 0.07 microflows of the current, and with the scan rate of 10 micro per second. So in that point of view, we get to know that with the biomass, we also can produce a sort of material which can be very helpful for our hydrogen evaluation reaction or for the water splitting. So this was the major things from my side, that how nanomaterials can incorporate in term of the different catalytical activities, and how we can overcome about the energy crisis in the developing countries, because this is the one of the very drastic reason that why what is the basic benefits of the conference is that we are right now together on a very major issue. We are here to discuss the major issue that we have to tackle, because it's our duty, because it is the basic duty of a researcher, of a scientist, of a student who is currently doing their research work, that you guys have to do something for your nation, for your country, for your future generation. Just to be in that scenario, you have to work hard in terms of basic tools, like why this conference is basic on the energy conversion. That why, because right now the major issues in the Asian countries is the energy crisis. So this is the basic aim, that what we have to do in our future. And these are my collaborators from the different countries. So I would like to say thanks to all of them. So even if you have any question, this is my WhatsApp number and email address as well. You guys can get to know more about energy conversion reaction and what we are doing in our research works. Thank you so much. I think the session is open now for the questioning.
Session is open for the questions.
I think so. I didn't take a lot of time of your conference.
Actually, it is a faculty development program, Professor, not a conference.
Okay.
Yeah, all who are attending here are the faculty members from the different institutions across India.
Okay. So I'm really sorry to say, like, students.
Yeah, sir. It's a faculty development program. Right from Monday, we are organizing. There are 13 sessions. Each session was handled by some resource person from some eminent institute like IITs, NITs, and also from the industry, industry partners. Yeah,
That's very interesting. And the next time I should be there physically.
yeah, definitely, Professor. We have planned some conference here, and definitely will call you as a keynote speaker during that time as a physical presence. Definitely.
With this reference to Professor Manoj Kumar, I would like to say to all of you that we are open for the collaboration. If you guys are interested, if you guys want to do some work for the energy conversions and batteries, my lab is open because I have three labs. One is in Pakistan, one in Italy, and one in Korea. So you guys are warmly welcome to come over there. Also, if you want to visit there, and also for the future collaboration, I'm completely open for the students as well and for you guys as well.
Most of the time, where are you available, Professor? Are you in Pakistan or Italy, Professor?
Mostly I'm in Europe.
Participants, you can please, if you have any queries, you please unmute and you can talk. Otherwise, you can put your questions in the chat box.
Good afternoon, sir.
Yes, good afternoon.
Good afternoon, sir. Sir, actually, the photovoltaic cell percentage, efficiency percentage may be in the range of less than 15%. If you use nanomaterials, how much it may increase,
Yes.
sir?
Okay. The photocatalytical efficiency. Like this is the one of a very interesting question for the wastewater treatment. Why this presentation was very short because the most of slides was on the wastewater, so I just cut them out, and I have no time to manage the more slide for you guys for the energy conversion because I was on the traveling. So okay, so what is happening like when you go for the photocatalytical efficiency? What is the basic mechanism? Like if you go with the sun drive, like light driven photocatalysis, so it can the basic photocatalytic mechanism will be actually the redox reaction. It have to reduce the organic pollutants or what you are thinking like pharmaceutical waste or reduction of heavy metals as well because you can't remove the dyes or the organic waste from the water. You have to degrade them. So the degradation efficiency can be increased like in like 70 to 90%. It can't go 100%, but 70 to 90% is achievable.
Okay, sir. Okay, sir.
And even in our recent research work, which was published, I think so, 3 months ago, we achieved 92% with the real time sunlight drive photocatalysis. If you want, I can share the article with you.
Okay,
Okay,
Professor.
okay.
If I'm right, Professor Palni is asking about the photovoltaic cell, Professor.
Yes, sir.
Photovoltaic
Photo.
cell.
Yeah,
Photovoltaic
yeah, yeah.
cell. I
Yeah,
was
yeah.
thinking about
Actually, the
that.
efficiency of the cell is almost around 15% only. So he's
Yes,
asking
yes,
whether
yes,
can we,
yes, yes,
with these
yes,
nanometers
yes,
can
yes,
improve that. That is what he's
yes,
asking.
yes, yes. They can improve.
Am
And
I right, Palni, Professor Palni?
Yes, sir. Yes, sir. You are
Yes,
right, sir.
yes, sir. Yes,
I'm
yes, sir.
sorry that I was thinking that it may be the photocatalysis. I'm sorry. Okay, for the photovoltaic cell, definitely the flow because you have to increase the energy density. If you increase the energy density, then the photovoltaic cell perform more because you actually need the transfer of electrons. If electron will transfer will be faster, you get more energy, and from photovoltaic cell you getting more energy. That is the basic reason to use the photovoltaic cell. So in that scenario, if you use the hydrothermal synthesized nanomaterial, that will be more good rather than the other one, because in that material you get more oxygen vacancies.
Okay, sir.
Is it clear?
Around the, yeah, still I'm having some doubts, sir.
Yeah, yeah, yeah,
When we
please
use
ask.
nanomaterials, many researches are going on around the world. Yet now we have only 15 less than 15% efficiency in photovoltaic cell.
Okay.
What percentage now the whole scientist community have increased the percentage? Sir?
The basic point is this, that you can increase the efficiency. Definitely you can increase, and there are a lot of research papers who are
Okay.
just on the my advice, just try bimetallic metal organic framework, and in the metal organic framework used ZIF 67, which you can synthesize with the cobalt and 2-imidazole, and in that you have to synthesize hydrothermally and then use it for photovoltaic cell. Definitely it will increase.
Okay, sir. Okay, sir.
And then you can change the reaction condition and temperature with your scenario, just for to get some optimum results. And if you get more concerns on this, I have my WhatsApp number, which you can take, and email as well. We can discuss as well. This is not a problem. This is a very easy task.
Okay, sure, sir. Sure, sir.
Is it clear?
Yes, sir. Yes, sir.
Perfect.
Okay, sir. Thank you.
You're welcome.
Any more questions from the participant side? Professor, I have a few questions on this.
Yeah. Please go on.
Yeah. So, as of now, what is the most promising nanomaterial with respect to the energy storage perspective, Professor? Thermal, very specifically talking about the thermal energy storage.
Okay. Right now, what was okay? If we are working on right now currently MOFs and magazines, and what difference we feel is that, like the cobalt nickel interaction with the magazine is the more interesting material in the energy conversion, rather than anyone else, even in rather than metal organic framework. Even right now, we are designing MOFs with magazine MX off, and I think so 1 month ago we published a review paper in Advanced Science on it, that how metal organic frameworks can incorporate with the magazine and can be a fruitful candidate for the energy conversion management. So you can connect MOF with magazine, but it's very tough. It's not easy. We are trying. We are even trying as well. We also succeed at some point, but it's really tough because you are dealing with the two difficult material. One is MOF, which is also unstable. Another one is magazine, which is really tough to design, and then etching it is very tough. So it's tough, but it's very promising material. Trust me, the magazine is very promising material in that scenario.
Magazine, I can't get, Professor. I can't get what actually it is. Magazine, I can't heard it before.
You can't get?
Magazine, Professor. What actually it meant for?
Magazine is the 3D material. It is the combination of carbide, nitride, alumina. Now what we do, we remove alumina from the magazine and we insert our metal into the magazine.
Oh, okay. It's a combination of nitride, carbide, and alumina.
Alumina. So in the
actually,
first
we heard
point,
about the aluminum nitride and aluminum carbide. That is different, but it seems to be a new material to us.
In the first point, when we buy a magazine, is carbide, alumina, and nitride. It's called 2D material, not 3D. So when we remove one layer from because alumina is in the center of that layer, that's the reason we called it a bed-like structure, just like a mattress bed. So we just remove one layer and we remove that alumina from that point and we insert our metal. So it's like you can say a very beautiful science of magazine that we incorporate even our MOFs inside in it. But in that scenario, it is a very unstable material. So you have to stabilize with the multiple etching and sulfonations. So it's tough, but it's very good material.
Apart from mass, what we can insert, Professor? Apart from
what?
mass, Professor, is there any other metal we can insert between the nitride
Yes,
and the
yes. You can insert nickel, you can insert cobalt, you can insert silver as well. Depend upon your demand. Like every material have its own specification. Just like silver is antibacterial. If you want to use magazine as an antibacterial material, definitely you have to incorporate magazine with the silver. You have to remove alumina, have to insert silver, but silver must be in that position in which alumina was removed. So the magazine should not know that alumina was removed from the layer, so the structure will not distort it. So it's like you have to steal something, but you have to keep something over there that I didn't steal anything.
Okay, Professor. But as far as in our country, this technology of for replacing alumina with other structure, it's very only a limited facilities are available here. That
You have to do the
people
etching.
like we can't access have access over.
No. Definitely, you will have not you will have not magazine as a 2D material. I can send you the material, the 2D material magazine, and you have to just do the etching with the hydrogen fluoride. The etching is that the surface will be removed, and exact after etching, you have to incorporate your metal nanoparticle, like silver. You have to add silver over there. So it's not a tough task, but it have to be managed on the time.
Oh, fine. Okay. Then have you throw some light on bio nanomaterial, Professor? Biological nanomaterials,
Okay.
presently what we people are doing is basically we are the mechanical people, and what we do is we actually purchase the nanomaterial, commercially available nanomaterials, because we are not having that much knowledge on preparing them by our own using salt gel or any other method. So what we normally do is we purchase commercially available nanomaterial having high level of purity, and we use them as a catalytic candidate with our material to improve the property. Say, for example, in my case, I am working on the phase change materials to improve their thermal conductivity and thermal storage without compromising the thermal storage characteristics. So what we do is we normally purchase the material from outside, and we incorporate those material inside the phase change material with the help of two-step process, with the help of ultrasonicator and other kind of physical equipment. And we
Okay.
do that, and we use that in some applications like water heaters or air heaters like that. So what we normally do. So can we suggest some methods so that we can also prepare our own nanomaterial without
Yes.
without
It's
depending
not
on the
a
external reagents?
it's
Yeah.
it's not a tough protocol to design biological nanomaterial synthesis, just like microbial synthesis or plant extract synthesis. So these are not so tough. These are very easy. You have to manage a rotary vapor if you have, and one hot plate. That's it. That is the basic instrument to design biological synthesized nanomaterial. For the microbial synthesis, you just need to purchase the microbial ingredients, and then you have to culture it. Even you will get the culturing microbe, and you have to just incorporate in your synthesis protocol. And you can get this synthesis protocol on our review as well, and even on our research paper as well. Uh, um I will after meeting, I will send you that 5 papers on that which are recent, that how you can design the green synthesized nanomaterial and how we can synthesize it. It's very easy. You have to first extract the plant, because in the nature, it's the natural thing. In the plants, the plants have metabolites, phenolic compounds, carotenoids, which act as a stabilizer, which actually makes nanomaterial to be in that shape. They control the size. So after that, material design, and it called as green synthesized metal nanoparticle. So you can design it. It's very easy. Rather than to purchase, you can design by yourself.
And one more thing, Professor, can we process the nanomaterials with the help of it by using some waste biomaterials like egg
Yes,
cells?
biomass.
Yeah,
Just
these are
like
all the
biomass.
products.
Biomass.
Yeah.
What you have to do with the biomass, you have to carbonize it, hydrothermally carbonize it, at least on a 400 500 degrees centigrade, and at the end you will get a carbon, only carbon, biochar, just like biochar. So that biochar can be used as a carbon material, and it's very efficient for the energy
Yeah.
because
Thank you.
it's very stable. The biochar is very stable.
So with the help of the biomass, right, Professor? What you
Yes,
are
with the help
suggesting is
of
to go with
biomass,
some
you can
biomass.
design. With the help of melamine, you can design. With the help of urea, you can design.
Have you worked with graphene, Professor?
Yes. We worked on in the previous. We worked a lot on graphene because graphene was the only material which was very active towards photocatalysis.
Yeah. For us also, it is having the maximum high level of thermal conductivity when we go for
Yeah.
incorporating them in some
I will just
thermal
give you
and
one point that take melamine, take 5
But
gram of
one more
melamine.
difficulty challenge what we are facing with graphene is, Professor, its cost. Again, we are again purchasing it
Telling
from the outside. Yeah. So is
I'm
there
telling you
any,
the
can
other
you
thing.
suggest some way to get them in a cheaper way with our own lab, Professor? Can you suggest some way to prepare
You
the
can get
graphene?
from me with no cost. I'm giving you another process. Like take the melamine, 5 gram of melamine, and put melamine in that oven at 400 degrees centigrade. After 4 hours, take out that melamine. The color will be changed. It will be yellow in color. First, it will be white. Then it will be yellow. It will be graphite, which is more active rather than graphene.
Oh, fine. But we need
So
something at the nanoscale, Professor. Graphite? So you are
nitrite.
suggesting to use the nanographite, right, Professor?
Yes. And even if you wanna take the graphene, you can take from me. We have a lot of graphene. We have a lot of biochar.
Yeah, what I'm suggesting, what I am expecting from you, if you suggest a method to fabricate the graphene in from our own laboratory, it will be helpful for us.
Yes,
Do you have? Yeah. If you
yes.
don't mind, you can suggest some method. If you don't mind, Professor.
Yes. I will. I will even send you some protocol on it, that how you can carbonize it, because you have a lot of waste. Change that waste into graphene.
Okay. Uh, can you show some case study like what we discussed now, Professor? From the melanin, we
Yes,
can do some process to get the. So
yes.
can you
Just a
show
minute.
some case study? If you have some case study, it will be useful for every one of us, Professor, who are out here.
Yes. Just one moment. I'm
Yeah.
just going to
A small
open.
presentation regarding the preparation of the nano from the melanin.
Yes.
It will be
Okay.
easy for us to catch the concept.
Awais. Mhm. Okay, please. Even now, I'm showing something to you. Okay, allow to share screen. Okay, I am on email. Again, I am on email. Okay, I just opened my Google Scholar, and the first paper is photocatalytical degradation of reduced graphene oxide based material. If I open this paper for you guys, can you see easily?
It's not. Yeah. Now it's visible, Professor. Yeah.
So in that paper, we this paper like we designed, we
Photocatalytic
get
degradation of malachite green and methylene group over reduced
yes,
graphene acid.
yes,
Based on
same
siloxanes.
like a lot of paper are presenting in my Google Scholar, like which are really focusing on exactly on this. This is also on the eggshell base activated carbon for degradation of methylene blue. So you can get this paper on my Google Scholar, and if you can't get it, you just send me the paper link. I will send the PDF to you guys. So there is already a lot of literature which you guys can see on my Google Scholar as well. Just
So-
for this, for that, how you can, even how you can produce the graphene. Also, we publish one paper on it, that from waste how you can carbonize it, and how then at then you will get a reduced and active graphene.
Okay.
First, you, because the coal is very cheap rather than graphene. The coal is very cheap. What you have to do, that is the coal.
Yeah. We can understand. What kind of coal, Professor?
Any type of coal, because
Any type of-
after the treatment you will get only the carbon. What is the graphene? Graphene is the carbon. But what is the main function of graphene is the activated carbon. That the carbon is activated to do the reaction. What we will do with the biochar, first we will, from the waste, we'll convert that waste into carbon, and then we will activate that carbon, and the same phenomena it will do. So this is the most easiest way, and you don't need to buy the graphene.
Okay. Professor, is there any other nano level 2D nanomaterial which is having a property almost equal to graphene, or rather than better than graphene? Is there anything available right now, Professor? People are talking about graphene. Yeah, I think
Still the scientists are addicted to use the graphene, because okay, C3N4, GC3N4 is very good material rather than graphene in some points, but at the end graphene wins the battle because it's the pure material rather than graphite. So still the scientists are working on that. Either we can shift to the C2N5, C3N5, just like these. So still it's in the progress. So hope so that if it works, so we will get to rid from the graphene. But still the graphene is the most valuable material.
so it's a combination of carbon and nitrogen, Professor. It's alternative.
Yes. Is C3N4.
What is the chemical name of that material, Professor?
It's graphite.
Graphite.
Okay. So they are thinking that it is more active in some point of view, just like some catalytical conversions. It's very good, but still graphene is stable one. So let's see if someone can make it.
Have you worked on any work? Have you involved in any work regarding the nanofluid, Professor, for the heat transfer? Nanofluids.
No. That was one of the field which I love to try, because one of our colleague was working on nanofluid thermodynamics, like turbulence flow and laminar flow. He is working on that, and he's right now in Australia, Sunmay University. So I have no expertise on nanofluids.
Okay. Your major area is on photocatalysis. Am I right, Professor?
Photocatalysis, energy conversions, energy storage devices, electrochemical workstations. This is basic my research area. And basic is to design and synthesize the nanomaterial with different protocols.
Okay, that's fine. So if any of your work is on lithium-ion batteries, Professor?
Yes, we work on lithium-ion batteries. We work on zinc-air batteries. We are working on sodium-ion batteries as well. And right now we are thinking on potash batteries.
Sodium-ion is one of the emerging kind of.
Sodium-ion is emerging one. Even the zinc-air batteries are very emerging. 4 months ago, we published a paper in GMCA about this, about zinc-air batteries.
Okay, what is the composition which we are using in zinc-air battery? It is new to us. Now only I don't know whether the participants are having awareness about it, but for me, it's a new one.
No. This is very open thing. I don't need to hide the stuff. This is very open thing. Like, okay, well, basically we are what we are doing. we are designing different sort of magazine for that again. So magazine in cooperation with the, because we get a zinc battery and we have to increase the efficiency of that battery. And what we are doing, we are using the material of magazine. And in that magazine, we are trying different composition, bimetallic, trimetallic, morph with bimetallic morphs, trimetallic morphs. Also, we are changing the ligands of morph as well. That maybe one day we will succeed to get more efficiency on a one point. So still we are in the processing phase of every time that, okay, we get results, but we are not getting more results rather than lithium. So that's the reason still lithium is more favorable battery in the world.
Is it zinc carries is still at R&D level, or is it commercial?
It's R&D level already. Yes, it's already in R&D level.
Okay.
But
What is
it's
the
not,
advantages
its market is not so high. Definitely the market is not so high. Still lithium have the more market because you know that right now even in Asia there is a lot of lithium still. So the reservoirs of lithium are very high rather than others. So still the scientists have focusing on the lithium rather than, but scientists also working on zinc, potash and sodium batteries. So let's see that which metal will win this battle.
Okay. So what are all the benefits or advantages
Because
of
the
zinc air
major
battery compared to the lithium based?
disadvantages of lithium, I will start from the lithium. Like the major disadvantage of lithium is the biosafety, because you are dealing with the lithium. But if you go with the zinc, zinc is very eco-friendly material because even zinc is essential for the human health as well. So in that scenario, zinc is a little bit better. But if you go with the sodium batteries, it is again one of a very precious metal for even human as well, and even for the battery cell life as well, because sodium metal have a very strong electronic configuration which make it very stabilized with the 11 molecules. So, and that's the reason that was the major concept for the potassium as well. But from my point of view, if we skip
But
lithium,
sodium is having a very high reactivity in the moisture level.
yes,
It's
if you skip lithium, then the next favorite battery, in my point of view, will be zinc air battery rather than potassium, because the moisture of sodium and potassium is higher rather than zinc. And even in the zinc, the molecules are very stabilized with the 30, because it's the electronic configuration is the full D block elements. So it's a very stabilized molecule already. So zinc air batteries can win this battle if it will be go in the social economic issues.
okay. Professor. What are all the basic elements which are in the zinc air battery, professor? Zinc.
In the zinc air batteries, what they are doing, it's just like, have you ever buy a dry battery?
Yes, professor. That is now we are commercially available in the market for every.
Yes.
Yeah.
What is actually the dry battery? The dry battery means that also it have the electrolytes, but the electrolytes leakage will not be done,
Yes.
because that's the basic reason it's known as dry battery. And what is zinc? And first we have to know what is air battery. Now the air battery is without electrolytes. It's electrochemical conducted.
Okay.
So this is the basic mechanism of zinc air batteries, that is without liquid. This is a solid battery.
Then what is the challenge to bring it to commercial
market? Still lithium have higher efficiency for sure. The lithium is very strong. Like your lithium is like, lithium is in +3, but in its actual state, and zinc is in its actual state, zinc is 0, because zinc shell is completed. So again the point is this, that the electronic efficiency and the current density will be produced more again with the lithium rather than with the zinc.
Okay. So the
So still it's
We have to
like
go far ways. Yeah, we have to travel a long
it,
way.
it still need 20 years to be in the exact market. When the lithium reservoirs will be finished, then zinc will be in the market. Before that, lithium can't go down.
Any other questions from the participant sides? The forum is still open to everyone. If anybody is having any queries or questions, please let us know. You can unmute your mic and ask, talk to our resource person. Otherwise, you can also put your questions in the chat box. I hope everyone is clear with what we are presented, Professor. Hope so. And Professor, one of our co-coordinator, Dr. Michael Joseph Stalin, is having some queries. So if you want to
Yes.
Yeah.
Yes. I'm listening.
So good evening, sir.
Hello, good afternoon.
Sir, I have one small doubt regarding with the nanofluids. Actually, I am doing research in the nanofluids. So I faced one problem due to the agglomeration. We are not able to get the stability of the nanofluids. So as a chemistry faculty, please kindly, so how to overcome the agglomeration of the nanoparticle in the particular fluids?
Okay, which protocol you are using? Like
So
co-precipitation?
we are using cerium oxide nanofluids. The cerium
Okay.
nanoparticles
And
mixed with water.
so how you are designing cerium? Like are you using sodium while synthesizing cerium?
No. Actually, we are purchasing the cerium oxide nanoparticle from outside.
Okay.
Then we mix it with the water. So we are facing
Okay.
the agglomeration, the biggest problem when you are doing research. How to overcome the agglomeration?
Okay. I will give you a very simple thing. You will not purchase cerium oxide. You have to purchase cerium nitrate, the salt of cerium. Are you listening? Is it clear?
Yes, sir. Cerium nitrate.
You will purchase cerium nitrate.
Sir?
Professor, are you there? Professor, are you there? Professor, are you audible?
Sir, you are able to hear me?
Professor, are you having any network issue? We can't able to hear you.
Yes.
Professor, are you there? Are you able to hear us?
Just
Professor, are you able to hear us?
Yes, I can hear you. That's
Yeah.
the reason this conference was organized about the energy efficiency, and I get the shutdown of electricity. So, what I was
Okay.
explaining. Okay, what I was
So
explaining
you
that.
got the question, Professor. You got the question
Yes.
from.
I'm giving the answer. Okay, the first you have to purchase the cerium nitrate rather than cerium oxide, the salt of cerium.
Okay.
And then you have to follow a protocol. You have to add nitrogen fluoride, NH4F, in that material, which will stabilize your particle. And it will be a 6 to 7 hour reaction. And after that, you will get cerium nanoparticles. and uh, and then you will utilize this material for nanofluids, and you
Yes,
will not get the
actually,
agglomeration.
for to overcome the agglomeration, we are using surfactant.
No. Don't use surfactants. Rather than this, it's more active because you will get the nitrogen fluoride NH4F inside of your material, which will make it more active rather than surfactants.
Okay, sir. Okay. And moreover, one more problem when you are mixing that nanoparticle into the water. So even though ultrasonicator, we are mixed continuously, so more than 30 minutes, and the
Yes,
particles are
yes.
not spread over entire the water. Some area the particles are stick together because when the particles stick together, so we are not able to get the Brownian motion in the better manner. So in that the heat transfer, the Brownian motion it is the proper only we can get the good heat transfer in chemistry. But the particles are stick to one particular area, it is not spread over entire area. So how to overcome that type of problem?
Okay. For that point of view, you have to utilize the mixture of 70-30%, in which the 70% will be methanol and 30% will be the water, and then again you have to put it into the sonicator, and it will be mixed in 3 to 5 minutes.
So that mixing is not an issue, but after 1 hour, 2 hours, even though whatever we are doing, it will be settled into the bottom of the that experiment.
Okay. Can you repeat it again?
So even though whatever we are adding all the things, but even after the sonicated 30 minutes or continuously, but after some time, after 1 or 2 hours, it will be certainly into the end because it is the whatever is the nano size is less than 25 nanometer. It is a solid particle. It will be settled down in the bottom of the experiment. It is the biggest challenge for overall using. So nano fluids, it is the biggest challenges to overcome the problem. It will settle
So
into the.
it's so it
Initially it is good. Initially it is good. After 1 or 2 hours, it will be because that is even though we are purchasing nanoparticle less than 25 nanometer, but even though we are not able
okay.
to avoid the problem of agglomeration.
So again, you are using cerium one, or you are using some other one as well?
No, copper, even CU, copper oxide, nanoparticle also, Al2O3 also.
Okay.
We
For
tried,
this,
we tried all the nanoparticles.
okay. For this, I will also ask Dr. Anjum, which is in Australia. He's working on nanofluids, and I think so he can give you the exact direction rather than me. From my point of view, what I can observe is that your particles are not stabilizing themselves for doing reaction in nanofluids. Am I right?
Yes, right, absolutely.
Okay. For I will text Professor Anjum, and I will send that query to Manoj when I get the answer.
And one more small question, sir. For our nanofluids research center, so the
Okay.
nanofluid, the particle ranges from 0 to 100. So when we are
Okay.
using 100, definitely we will get more pumping power and all. We will get more pumping power, and moreover the pressure loss also will be more. So for that, it is optimum. You have to use from 0 to it is 25. It is the good for the for better heat transfer. So for that, which is the best method to prepare the particle sizes from 1 to 25 nanometer size, which is the best method for your as per your
Okay. There are
concern.
two methods in which you can get some good result in term of the size. Number one is hydrothermal method, autoclave method, and the second method is the microwave irradiation method, in which you will get these required size, and the third is also one of a very good method is the green synthesis approach. You can use the microbial synthesis method, and you will get the size lesser than 15, not even greater than 15. It will be lesser than 15, or you can design quantum dots, but it's very tough.
It is a costly material. Sir.
Yeah. Quantum dots also they cost a lot. So the microwave method is more cheaper, and microbial one. Hydrothermal also a little bit expensive.
Okay, sir, thank you. So, a participant having any queries related to this particular topic, please raise your questions to the research person, please.
I will also ask Anjum for your query, and I will let you when he will answer.
If any queries from the participant side, so please let us know. Otherwise, you can wind up the session. Professor, once again, we thank you so much for joining with us and spending your valuable time with us, even with the challenge of not having electricity. You are answering our queries passionately. Very happy to have you.
Thank you so much for inviting me. Yeah, I told you that I was in Pakistan, so this is the major issue in our countries, that the electricity.
Yeah, I thought you are an Italy professor. Yeah.
Yes, I will be back like in 3 days. I will have flight on Wednesday, and I will be there in Italy on Thursday.
Okay,
But until
professor.
there, I will be here.
Is there any possibility for us to come and meet you in Italy, professor? Do you have
Yes, you guys can
any
come
program like
to.
fellowships and all to come and visit
We
your
have
laboratory for a week or for a month of period?
Okay, we have every year we have a call in the start, like
Okay.
in January, we have a call of visiting professor and postdocs. Every year in the
Oh,
start, like in the January, we have the call for
okay.
visiting professors and for the postdocs. We hire every year two visiting professors for one month and one postdoc for every year and for 1 year.
Okay, professor. You please
So
let
you
us know
guys are.
so that myself or anybody from our participants will get benefit out of it, so that there will be a mutual benefit between the Italy and
Yes.
and as well as Parasans.
Whenever it came, I
We
will
also,
share
yeah.
the things with you guys as well. And in Korea again, the same. We will have the call in Korea in the mid of March for the
Okay,
distinguished
professor.
visiting professor.
Yeah, that's promising. It's promising. You
Yeah.
please let us know for any opportunity regarding that, so that our people also have some collaboration with international professors,
Yeah.
eminent professors like you.
That's what
Yeah,
I said already in the start of the meeting, that I am open to collaborate. We can design some mutual project. We can work together on the mutual grants as well. So you guys are welcome.
thank you, professor. Thank you for your kindness. And on behalf of the Department of Mechanical Engineering, Madhushangra deemed University, and on my own behalf and on behalf of the participants, I once again thank you for spending your valuable time with us and patiently listening our questions and answering our questions. Thank you, professor.
Yeah, always welcome, sir. Always welcome. Thank you so much.
Thank you, professor. Have a great day.
Bye bye.
Bye, professor. Thank you.